Here is a bet you should never take. Grab any big pile of real-world numbers, the populations of every country, the length of every river, the dollar amounts on a year of bank statements. Now look only at the very first digit of each number and count how often that first digit is a 1. Your instinct says it should be rare. There are 9 possible first digits, 1 through 9, so a 1 should show up about 1 time in 9, roughly 11%. That feels obviously right. It's wrong. In real data like this, the first digit is a 1 about 30% of the time, nearly 1 in 3. Almost a third of the numbers start with a 1, and the bigger digits get rarer and rarer until a leading 9 turns up less than 5% of the time. This lopsided pattern is a genuine mathematical law. It's so dependable that when a set of numbers breaks it, investigators start to suspect those numbers were faked. Let me show you the fingerprint hidden inside honest data. The pattern has a name, Benford's law. And the strange thing is how specific it is. It doesn't just say low digits are more common, it says exactly how common. 1 leads about 30% of the time, 2 about 17, 3 about 12. And it keeps sliding downward in a smooth curve all the way to 9, the rarest, down under 5%. What's eerie is where this shows up. It's not a quirk of one kind of data. Count the first digits of the world's country populations, Benford. The lengths of the world's rivers, Benford. Physical constants in a science textbook. The dollar figures in a company's accounts. The street numbers in your address book. Even the numbers printed on the front page of a newspaper. Wildly different sources, measuring completely unrelated things, all fall into the same lopsided pattern of first digits. It looks like a coincidence that couldn't possibly be a coincidence. So why does the universe of numbers lean so hard on the digit 1? The clearest way to see it is to think about growth. Imagine an investment that grows by roughly 10% a year, starting at $1,000. To climb from 1,000 to 2,000, it has to increase by a whole 100%. That takes years, and for all those years, the balance starts with a 1. But once it reaches, say, 8 or 9,000, it only needs to grow a little to tick over to 10,000 and start with a 1 all over again. The number spends far more of its life with a low leading digit than a high one. It lingers on 1 and races past 9. Almost anything that grows by multiplying, money, populations, city sizes, behaves this way. And there's a deeper reason underneath. A pattern this universal has to be blind to the units you use. The lengths of rivers follow Benford, whether you measure them in miles or kilometers. But changing units multiplies every number by a fixed amount, and it turns out the only distribution of first digits that survives that kind of rescaling unchanged is Benford's exact curve. The law is what's left when the pattern refuses to care what units you picked. Now here's where it stops being a curiosity and starts catching criminals. Genuine financial records, thousands of real transactions, invoices, expenses, tax figures are built up from countless natural multiplying quantities. So they obey Benford's law almost perfectly. The leading digits of a company's honest books curve downward from 1 to 9 exactly the way the law predicts. But when a person sits down to fake those numbers, to cook a set of books, invent expenses, fabricate results, they almost never reproduce the curve. Human beings making numbers up tend to spread the first digits around too evenly or cluster them in the middle, reaching for 5s and 6s and 7s to look random. They don't put a 1 in front nearly often enough, and that leaves a signature. A forensic accountant can take a suspicious ledger, tally up the leading digits, and lay them against Benford's curve. If the real data bends away from the law, too few 1s, too many middle digits, it's a red flag that the numbers may have been invented. Tax authorities and fraud investigators use exactly this test to decide which books are worth a closer look. The lie shows up not in any single number, but in the shape of all of them together. Now, a caution because this is powerful but not magic. Benford's law only works on the right kind of data, Numbers that range across many sizes, from small to enormous, and aren't fenced in. It does not apply to things like human heights, or IQ scores, or anything clustered tightly around an average, or numbers that were assigned rather than grown, like phone numbers. And a deviation from the law is never a verdict. It doesn't prove fraud. It only says, something here is strange. Look closer. Point it at the wrong data, as some have with election results, and it will happily mislead you. But where it does apply, it reveals something quietly profound. Real, unplanned, organically generated data carries a hidden statistical texture, a fingerprint left by the way the world actually produces numbers. And a forger, focused on making each individual number look plausible, almost never manages to fake the texture of the whole. Truth, it turns out, has a shape, and that shape is very hard to counterfeit. That's the fine print hidden in a page of ordinary numbers, and reading it is exactly what this channel is for.